All right, we're going to talk about the situation where a projectile is launched at an angle, which I think I called angled launch on your pacing guide. How is that different? Well, when you have a launch that's at an angle, you have your launch velocity, which is going to have a magnitude. That's like just how fast it's going. You can call that the speed. It doesn't care about direction. And an angle, right, that it's launched at. Here, let's call this V. And I'm going to make a big note here. This is at an angle, so note that V is not equal to VI. And V is not equal to VF. And V is not equal to Vx. It's not equal to any of those things. Now when you set up the problem with your vertical stuff and your horizontal stuff, that number is not going to show up anywhere here. Why not? Because this number is not vertical and it's not horizontal. It's some of both. So we have to split this up so that we know what goes where. Of course, that's going to be -10, unless you're working on another planet. And VI, VF, delta Y, and time. And on this side, we're going to have Vx and delta x and time. And of course, you know you've done enough of the horizontal launch problems, I hope, at this point, that you understand that here we use kinematics equations to relate these things, and here there's just one equation, that delta x is equal to Vx times t. So there's my three. There's VI, VF, and Vx. But this number, whatever it is, does not go in any of those places. So what do we do? Well, we know how to do vector stuff. We take this V and we break it up into the horizontal part and the vertical part. So this right here, whatever this is equal to, that's the Vx, which is constant. The horizontal velocity is constant. And whatever this is, that is my VI. That is the initial vertical velocity. And how do you find those things? Well, the same way that we do trig all the time. This right here, this VI is opposite of this. So VI is equal to whatever V is times the cosine. Sorry, this is opposite, so that's sine. Excuse me. So VI opposite that angle is going to be V sine theta, and Vx, this right here, is adjacent to that angle, so that's going to be V cosine theta. So you're going to find those two things. You're typically going to know this number and find those two things, and those are the things that go into these places right here and here. So VI is going to be equal to V sine theta, whatever that is. You're going to have a number for that, and Vx is equal to V cosine theta. And then you do math. One thing I just want to make sure that we understand, I'm going to do one example for you, and make sure that we know how to do to solve quadratic equations with our calculator. I think I've used my calculator for you to do that, but I'm going to give you one example in this, specifically in this context. So let's say we have a situation where we have one of those cliffs that we kept launching things off of, but this time we're going to launch something at a speed of, let's say, 20 meters per second, and let's say this angle is 30 degrees right here. And I want to know where does it land? Right on my enemy's castle. Well, let's see where it's going to land. So that's trying to find the delta x. So the very first thing before I do anything else, what I'm going to do is make a nice big picture here. There's my 20 meters per second. I need to break that into the horizontal and vertical parts. The arrowheads are important here because it's possible that you could have something that's launched like downward at an angle, and that's going to make this negative, right? In this case, I've got positive, positive. So I need to do, going to just make sure that I'm in degree mode. So 20 times the cosine of 30 degrees is about 17.3 meters per second. And then 20 times the sine of 30 is a half, so that's going to give me 10. Okay. Now I'm going to set up my little lists here. Acceleration, initial velocity, final velocity, delta y. Oh, I forgot to tell you how high the cliff was. Let's say it's, I don't know, 50 meters? 50-meter cliff. And time in the horizontal direction, I've got my Vx, my delta x, and my time. Of course, the time is the same for both, because it's only one thing there. So this is always negative 10. My VI, this is a vertical. Vertical initial velocity, that's this. You can add that to your diagram if you want. 10 meters per second. Nothing to do with that 10, right? Let's finish here. VF, don't know, don't really care about that right now. Delta Y is, it's going to go from here to here. If you're not careful about your signs, it's so easy to forget that needs to be negative. It's going from here down 50. Over here, my Vx is 17.3 meters per second. That is the constant horizontal velocity. And that's all I know over here, but I can find the time here and then bring it over here. So that is what we're going to do. So to find that time, I'm going to use this equation. I'm going to write down that equation first. Minus 50 is equal to 1/2 times a, negative 5, just like it always is. And then VIT. In all of our horizontal launch problems, this was 0, right? Because my initial vertical velocity wasn't any. And now I've got something there. Okay, so what do you do with this? Maybe you're itching to flex some algebra muscles. I don't know. I suppose you could try to factor it. But a lot of the times, including with this one, I think, it's just not going to factor. So what do we do with that? We are going to use our calculator. I guess the little bit of algebra, if you're really just itching to do some algebra, you added 50 to this side. If you mess up that sign, well, that's a game over, basically. So you got to be careful. So I'm going to go to my y equals, and I'm going to put in minus 5x squared plus 10x plus 50. Right? And then before I hit graph, I'm going to do that in a second, I'm going to go to my window, and let's just pretend that you had your calculator in like regular old standard window. Oh, I didn't mean to look at it yet. Don't look. And then you pushed the... So when you push the window button, it looked like this. Or where do we want to look? This is what I recommend to you. The x's are really the times, right? So I don't need to be looking at negative times. So I'm going to make my x minimum 0, and my x max is 10. 10 should be fine. Every once in a while you might see a problem where you have to go a little bit past 10, maybe turn that into 20. But for something to be in the air for 10 seconds as a projectile, that's a long time. We're not going to see too many numbers bigger than that, but it's possible. And then it really doesn't matter what your y minimum and your y maximum are, so long as you've got going negative to positive. So long as you can actually see the x-axis. In other words, you're going from a negative y up to a positive y. So I'm just going to leave that at negative 10 and 10. That will work fine. And I'm going to graph. And that place where it crosses, since I have this is the thing that I graphed, and I'm interested in where it crosses because that's when it's equal to 0. And so it looks like it's 1, 2, 3, like 4 and change there. But if I want to find it exactly, or find the calculator's best approximation of what it is, I'm going to go second, calculate. That's second, and the button that says trace there. And I'm going to go to the zeros because I'm trying to find the zeros, or the 0 in this case. So I'm going to scroll down to that and hit enter, or you can just hit the number 2. That will do it also. Okay, now the calculator is going to ask you for left bound, right bound, and then guess. It's going to prompt you 3 different times. For me, you could try to guess. There's a little game you can play with the arrows here. Don't do that. That's just a waste of time. You can type in the left bound, the right bound, and that will save you time. I think it will be more efficient and more accurate. You won't get frustrated with not knowing where the cursor is. So where does this cross? It looks like between 4 and 5, but you know what? I'm not even going to take any chances here. I know for sure it crosses between 0 and 10 because those are my min and my max. And so I'm just going to use those. Left boundary, 0. Right bound, 10. And then you have to hit enter one more time. I don't know why it does this last prompt here, but it does ask you one more time to hit enter. So just you don't have to type anything when it says guess, just hit enter again. And then it's going to find that for me. So it looks like my time is about 4.3 seconds. There's nothing that you have to show. If you're doing this like on a test, there's no work to show. You just did this with your calculator, right? Well, there's my time. If you're wondering, like, why do you have to do that left bound, right bound thing, it's because of the way a calculator is just a dumb machine that very literally follows instructions. So it needs to know exactly where you want it to look for that for the 0, because we could have something that crosses more than one time. We are not going to see that, but it can happen. Actually, we are going to see it sometimes, so you have to tell it where to look. Here's my time now. So once I have that, then the equation that relates these things is delta x is equal to vx times t. So my delta x is equal to 17.3 times 4.3, and gives me about 74.4 meters. That is how you do it. I'm just going to give you that one example. You're going to have plenty of opportunities to practice that. If you need to come back and watch this one again, then do it. If you want to, here's a good thing to do. Set this problem up and then shut the video down, put your notes away, and see if you can reproduce everything that I did there. And then you'll be in good shape. Okie dokie.